Okay, ladies and gentlemen, welcome to today's video lesson for chemistry. So what I'm going to do is I'm going to review some of the most important concepts of the pages that were discussed in class today. And hopefully this will be enough for you guys to to refresh a little bit of what we did. So today we started talking about electron configuration. And in the last chapter, we had discussed or we had mentioned that electron configuration pretty much, or that, I'm sorry, the quantum theory had pretty much, I wouldn't say disproven Bohr's theory, more as found uh, found Bohr's theory, or modified or improved on Bohr's theory. So today we're going to review some of the concepts. Now, just so you understand, the quantum theory basically proposed that the atom was not neatly floating around the nucleus, but that the electrons were in orbitals, in three-dimensional structures, um, and that not only was the position of the atom a characteristic, but also the energy that they possess. So based on that, let's go over some of these points real quick. It says the quantum model of the electron better improves Bohr's because it describes the arrangement of other atoms other than hydrogen. Remember that one of the limitations to Bohr's theory is that it only talked about hydrogen, and it was hard to prove that when we work with other elements other than hydrogen. So the quantum theory actually is able to prove how that would work with other elements. It says that the arrangements of electrons in the atom is called the arrangement of the atoms in an electron is called the electron configuration. The way the electrons are arranged in an atom is called the electron configuration. It says that the electron configuration is also unique for every atom. So the electron configuration is basically how atoms are arranged, and that is going to vary or depend on what element we're dealing with. Okay, it says that and we have certain principles and rules that help us understand a little bit of this. So the first one says is called the Aufbau principle. It says the Aufbau principle states that electrons occupy the lowest orbital that can receive it. So basically, what the Aufbau principle is stating, and again, this is just building on the fact that one, electron configuration is how the electrons are arranged in an atom. Two, that each atom has a particular electron configuration. Now, building on that, we have three or four rules. And one of the rules is the Aufbau principle, which states that atoms occupy the lowest possible orbital level. Okay. And it says that the orbital with the lowest energy is the 1s orbital, and the orbital, and then the 2s orbital is the next highest in energy, followed by 2p. So basically, what this is stating is that, well, we have 1s, which is the lowest one. After we're done with 1s, the electrons are arranged in what is called a 2s orbital, and then followed by the 2s orbital, they are arranged in 2p. Now, if we go back to the previous video, we said that p actually had 3 orbitals. So that means that there are actually 3 lines. Okay, so basically what the Aufbau principle is stating that the electrons are going to be in the lowest possible state, which in this case is the 1s, after they have occupied the 1s. Give me 1 second, guys, sorry. After they have occupied the 1s, they're going to go to the 2s. And after the 2s orbital has been occupied, they're going to go to the 2p orbital. And the 2p orbital has 1, 2, and 3 sublevels in which the electrons can be arranged. And we're going to see this when we talk about the example at the end of the lesson. But basically, so you guys have an idea, 1s is the lowest, followed by 2s, which is the second highest, I guess, or the second lowest, however you guys want to say it, and then followed by 2p. And the s orbitals have 1 sublevel. The p orbital has 3 sublevels. And as we go on further in the section, we're going to talk about d and e sublevels. But for this video lesson, we're only going to focus on those. So with that in mind, guys, let's continue reading and going over some of the principles. So let me erase this real quick without deleting the paragraph that I wrote. Okay, so that being said, let's continue on with the remainder of the lesson. So we know that they goes from 1s, 2s, and 2p. The next rule that we're going to talk about is the Polyexclusion Principle. And the Polyexclusion Principle states that no two electrons in the same orbital or the same atom can have the same set of 4 quantum numbers. That means that the quantum numbers for every element is different. The quantum number for every element is different, and we already talked about the quantum numbers in the previous video. Okay, so just remember, no two elements can have the same 4 quantum numbers. If we move on, it says that the third rule requires placing as many unpaired electrons as possible in separate orbitals in the same sublevel. That means that, for example, if we know that the lowest possible sublevel is 1s, and let's say we're talking about helium that has 2 electrons. So let's go over that. Let's go over that real quick. If we talk about helium has 2 electrons. So basically what it's saying, what this rule is stating, is that helium, which has 2 electrons, and if it has 2 electrons, it also means that the number of electrons is the same as the number of protons. But anyway, helium has 2 electrons. Now, what this rule is stating, the third rule, which is known as, which it states that the third rule requires placing as many unpaired electrons as possible in separate orbitals in the same sublevel. Hund's rule states that orbital of equal energy are always occupied by 1 electron. So the third rule is Hund's rule, okay? And Hund's rules basically says or states that orbitals of equal energy are always occupied by 1 electron before being occupied by a second electron. All electrons in subsequently occupied orbitals must have the same spin state orbital notation. So, for example, if we go, what this states is that if we have helium and helium has 2 electrons, that means that I cannot say, well, 1s1, right, and then go ahead and go and skip from the 1s orbital to the 2s orbital. Okay, I can't do this. According to Hund's rule, that's not possible. I cannot have, if helium has 2 electrons and the lowest orbital is 1s, that means that both electrons have to be, let me get the spotlight. So we know that helium has 2 electrons. So according to this rule, it's stating that I cannot do this. This is not possible. I cannot have 1 electron in the 1s orbital and then just go ahead and skip to the 2s and add another electron there. That is not possible. What Hund's rule is stating is that if helium has 2 electrons, both of the electrons have to be in the same orbital with opposite spins. Now that means that both electrons have to be in the 1s orbital, not have them separated in the 1s and the 2s. They have to be in the same orbital. So this is not possible according to Hund's rule. So to fix that, to avoid that, what is done is simply that if helium has 2 electrons, then they're both going to be in the 1s and they're going to have opposite spin, meaning that one electron is going to have, or one of the arrows is going to be written facing upward and the other arrow is going to be written facing downward. That's what the opposite spin means, that the electrons are facing opposite direction. And the rule says that in order If I want to go to 2s2 or to 2s to the 2s orbital, the rule also states that if I want to go to the 2s orbital, the first one has to be fully occupied. So the rule also states that if let's say helium had a different number of electrons, let's say it had 3 electrons or 4 electrons, although that's not the case, but just for argument's sake, if helium had more electrons, that means that in order for me to go from the 1s orbital to the 2s orbital, this sublevel has to be fully occupied. I cannot go to another sublevel or orbital unless the I cannot go to another orbital unless this sublevel is fully occupied. So in the case of, if this were true, then I could go to 2s because 1s is already occupied. Okay, so that's what basically the third rule is stating. So let's go ahead and continue with the video lesson. I'm trying to erase this and I'm being as careful as possible so I don't erase anything important. So let's go ahead and then let me get my spotlight again to point out where we left off. So again, and this third rule is called Hund's rule, which says that in order for electrons to go from one orbital to another, it has to be occupied in its entirety, and the spin states have to be opposite to each other. Now, what you saw that I did when I drew the arrows and I was talking about heliums and the electrons, that's called orbital notation. So let's go ahead and read a little bit about orbital notation. It says that orbital notation is orbital notation is used to arrange electrons or to write up electron configurations. Now, for example, orbital notation is what I was doing when I was explaining the helium example. 1s, 2s, 2p, which we know has 3 sublevels. Okay, and of course we have the D sublevels, and we're going to talk about those later on. But basically, this is what orbital notation is. Orbital notations is basically writing the electron configurations, kind of like a staircase as it goes up. Okay, and another thing about orbital notation is that when basically an unoccupied orbital is expressed like with a line like you see here and its name. So this would be the 1s orbital, this would be the 2s orbital, and this would be the 2p orbital. Okay, so if they're unoccupied, they would be just represented with lines. It says with the name underneath. It says an orbital occupied by one electron is represented by an arrow. So we talked about helium. Now let's talk about hydrogen for a minute, because that was the original element that was used by Niels Bohr to propose his electron arrangement theory. Now let's say we have hydrogen. Hydrogen has 1 electron right here, hydrogen. Okay, hydrogen has 1 electron. So normally hydrogen will only be at the 1s orbital, and it will only occupy 1 sublevel. So basically, hydrogen would have a configuration of 1 electron, and when 1 electron occupies an orbital, and more specifically a sublevel, it is represented with 1 arrow looking upward. Now, in the case of helium, which we did a minute ago, helium has 2 electrons. So helium has 2 electrons. And in the case of helium, we have a 1s orbital, but instead of having 1 electron represented by an arrow looking upward, we have 2 electrons with opposite state or opposite spin, which means that one of the arrows that represents the electron is going to be facing upward and the other one is going to be facing downward. So that's why we have the configuration of hydrogen. It's because hydrogen only has one electron. Sorry, guys. I thought I had my spotlight on. Here we go. Because hydrogen has one electron, we say that it is 1s1 and it has only one electron with this spin state. Helium has two electrons, and in this case, we have one s orbital with two electrons with opposite spin. Okay. Now, with opposite spin, configuration eliminates or electron. And so we talked about orbital notation, which is this. This is referred to as orbital notation. Now we're going to talk about electron configuration. Electron configuration eliminates the lines and the arrows. A superscript is added to the hydrogen as a configuration of 1s1. The superscript means the hydrogen has one number of electrons, and means one electron is added to the 1s orbital. There's a mistake there. It's supposed to say 1s orbital. So let's see if I can erase that. The 1s orbital. So basically what this is saying, let's see if I can erase that. And instead of write 12, write 1s. I apologize for this. Okay, let's see if I can do it now. Okay, so what the electron configuration does is that it eliminates the arrows. The orbital notation, which is what I did first with the configuration of hydrogen, which has one electron, and helium, which has two, the arrows, the representation of the arrows are called orbital notations. So electron configuration is kind of the opposite. Well, not the opposite. What it does is that it eliminates the arrows and it eliminates the lines. And for example, and we're going to continue to use helium and hydrogen to illustrate this. So as I mentioned before many times in the video, hydrogen has one electron and helium has two. So the electron configuration of helium, because it has two electrons and because it only occupies the s orbital, we say that the electron configuration of helium is 1s2. 1s just means that it is in orbital 1s, and the 2 just means that helium has two electrons. In the case of hydrogen, hydrogen only has one electron, so the electron configuration for hydrogen is 1s because it only occupies an s orbital, and 1s1. And the reason why it is 1s1 is because the reason why it is 1s1 is because it only has one electron. Okay, so that being said, let's go into the sample problem that is in your textbooks, and hopefully this will clarify any doubts that you have. And if you have any questions at the end of this video, you guys know where you can find me. So let's go ahead and read the problem. I'm just trying to erase this and avoiding erasing any important piece of information. So, and let's move on real quick. Okay, so the electron, it says, the problem says the electron configuration of boron is 1s2, 2s2, and 2p1. The question, let me get the spotlight, says the electron configuration of boron is 1s2, 2s2, 2p1. There are two questions, and the other one is basically telling us what we're going to do. One question says, how many electrons are present in boron? What is the atomic number of boron? And write the orbital notation of boron. So let's do the first one. A is asking us how many electrons are present in boron. Now we have the electron configuration. So all we're going to do is first write the electron, or pass on the electron configuration that the problem gives us. And they're telling us that the electron configuration for boron is 1s2, 2s2, and 2p1. Now, guys, we do have other orbitals besides S and P, and we are going to see those later on in this section. And we even have other types of notation when we have really large orbitals occupation. So in the case of 1s2, 2s2, and 2p1, what we're going to do is we're simply going to find the number of electrons. We're going to add the electrons. We are going to add the electrons. We have 1s2, 2s2, and 2p1. So to find the number of electrons, we're going to add the exponents. We're going to say, well, 2 plus 2 is 4, plus 1 is 5. So we know that boron has 5 electrons. So we answered A. Now, the second question is asking us to find the atomic number of boron. Now recall from chapter 3 that the atomic number is the same as the number of protons. So we know that the atomic number is the same as the number of protons, and the number of protons is equal to the number of electrons. So if the number of electrons that I have for boron is 5, that means that the protons that I have is also 5, which means that the atomic number is 5. So when you find the number of electrons, remember that the number of electrons is this equal to the number of protons, and remember that the number of protons is equal to the atomic number. So we have, in this case, 5 protons. With that being said, now we can do the last part of the problem, which is the orbital notation. Now remember, the orbital notation is different from the electron configuration because the orbital notation represents the arrows. And I'm actually going to leave the A there, so that way we can do the electron, or use the electron configuration to do the to actually do the orbital notation. Let me just erase this. Okay, so according to the electron configuration, it is 1s2, 2s2, and 2p1. Remembering that the lowest orbital that every electron, that every element has, or every atom has, is 1s, and remembering that that S has one sublevel, and each sublevel occupies 2 electrons. So the first thing that we see is that our electron configuration is 1s2. So that means that the 1s orbital is going to have 2 electrons. Remember, the arrows represent the electrons, and they're going to be facing opposite direction, and that represents the opposite spin. So there is the 1s2, which is the first orbital. Now it says 2s2, so that means that once the 1s orbital is occupied, I'm going to go ahead and move on to the 2s orbital, and it's saying 2s2, which means that the 2s orbital is also going to have 2 electrons, or 2 arrows in this case, representing the electrons, and the arrows are going to be facing, or have opposite spins. So 2 electrons in the 1s orbital, 2 electrons in the 2s orbital. Now that they're fully occupied, we're going to go to the p orbital, which has 3 sublevels. Remember that the sublevels are represented by the lines, and it's 2p. Now, there is 1 electron in 2p. So literally, it is going to occupy 1 electron, and when we have single electrons, like in the case of 2p, that it just has 1 electron, remember that we simply write it as an arrow in this case, which is looking upward. And because there is only 1 electron occupying the 2p orbital, we simply write 1 arrow in the first sublevel facing upward. And guys, this has been your introduction to electron configurations. Hopefully this video will clarify any doubts, and we'll see each other in our next class. Bye.